last time? You didn't? Pass this back. Okay, so I'm looking at this chart on the last page, and I didn't have room to cut it all, to copy it all, but let's just consider these 4 cases, which are probably enough. So I guess the first idea is this polygon edge. And here is a polygon like this. Maybe I'll do it like that. Nearly vertical, right? So if I have columns of pixels like this, probably I should have used different colors for the edge and my pixel column. It's going to be jagged, right? Say this is white and this is black. So this pixel's black, this pixel's black, this pixel's white, this pixel's white. And if I continued it on down like this for a few more pixels, eventually it would move over. The white pixels would maybe start in the next column somewhere. Okay, so at this point, this pixel center is white. So my white region is going to look like this. These are going to be white. These are going to be white. And then I have another collection of white here. And the boundary between them is this very jagged line. And it's going to go on like that. So that's the jaggies we're trying to avoid. So suppose, so let me write this, the result. So I have a jagged edge. So this is one pixel center sample. I have a jagged edge. And the next example I want to talk about is, maybe I'll put it on this board. Here is my pixel array. I should have probably pre-drawn these pixel arrays instead of pre-wrote my other stuff. And I have an infinitely thin, what did I say? Nearly vertical, infinitely thin line. So I have the same, it's not a polygon edge, it's an infinitely thin line. And I'm sampling it at the center of each pixel. If it's infinitely thin, even if it's infinitely bright, it won't contribute. It's like a delta function thing here. But it's basically not going to show up at all unless it just, happens. The probability is 0 if it was chosen a randomly line, but if it's a human specified endpoints, probably the probability is higher that one of those endpoints will be exactly on a pixel. But basically, the line is missing. Okay, and even if it's moving, at any given frame, it's on one of these random positions. So it's probably missing. I guess one thing that I didn't write even in the table I handed out is what happens if this polygon edge is moving slowly? These jaggies are going to crawl up the line, right? Unless the line is exactly vertical, that polygon edge is exactly vertical, in which case, even though the data says it's supposed to be moving smoothly, it's going to appear to jump one column at a time when of that exactly vertical line each crosses the pixel centers. And a nearly vertical line 1/10 of a pixel wide, what's that going to look like? If it's sampled at the center of the pixel. So basically what that says is I make this line a little bit wider. Right? So it's I don't know if it's exactly a 1/10, but 1/10 of a pixel. 1/10 of a pixel. You know, basically, on the average in one column in 10, it's going to show up. So you're and you know, somewhere down here there's going to be another one, 1/10 of those rows. So 1 dot every 10 rows. Okay, so this certainly demonstrates that anti-aliasing is necessary. And one anti-aliasing method is just what they call supersampling. There's an OpenGL multi-sample option like that, which takes more than one sample per pixel. I think usually it would take 16, but since I wrote on the sheet 4, let's just take 4. 4 subpixel center samples. Okay, so what's going to happen to this edge then? If I take 4 samples here in the center of each subpixel square. In that case, for this square, I'll have 2 of them will count, and then I'll average it, and I'll get some sort of shade of gray, which is halfway between the full white and the full black. On this one, maybe of those 4, maybe if I don't know exactly how it comes, but maybe 1 in 4, so it's a fainter shade of gray. In this case, maybe 3 or 4. If it's almost vertical, then it's probably going to be by 2s. Right? So it'll still be a little bit jagged. There'll be long stretches where it's the same, and then a short stretch where maybe 1 was covered more. So it'll still look jagged. There'll just be really only 2 of the 5 shades, 3 of the 5 shades, black, half white, and full white, and then occasionally you'll be lucky enough to get it to split like I pretended it did in this case here. So the jaggeds will be partly cured, and if I think you have a circular arc that's not nearly vertical, well, most places you will take advantage of those 5 different colors of gray. So how shall I say it? In general, we'll have an anti-aliased, I'll call it partially anti-aliased edge. Usually using the 5 colors with the fractions, but with this almost vertical edge, but here mostly only 3. Okay, for this infinitely thin line, the line is still missing. Right? Because even those 4 subpixel samples, it's not going to see. Moving vertical line, still missing. And what about now? This will be 4 possible places. It's thin. It's probably in a given pixel going to cover only 1 at most. So mostly 4/10 of rows have intensity 1/2, but occasionally, if it's lucky, some of the rows might have an intensity, a quarter, right? Because one of those 4. But again, if that 1/10 strip is lucky, where is it? Maybe, maybe it's this one. Could line up enough that this was on this edge and that was on that edge. Occasionally, you might have 2. Rarely intensity 1/2. I should have written intensity here. And I guess if that happens, it's going to make up by missing even more on other rows, because it's still got to add up to 4/10 on the average. Okay, now, I didn't have a column for jittered subpixel samples. But what is that going to do? Since I thought about it, let me add it here. Here, because they're jittered, I think you're more likely to be able to get other numbers more often, right? Because even though that edge is almost vertical, because the samples wiggle a little bit, you'll get more use of 5 colors, but more noise. Because in some places, depending on how they fit, let's go here where this edge is now here. So in each of these quarters, I have a subpixel sample. It may be that in this quarter, my subpixel samples turn on, so it would be a half. But in this case, my subpixels might all be outside, and it actually goes, even though it should be getting brighter, it might have gotten darker here. So that's what I mean by noise. Let's see. The line, they're only point samples, right? So it's still probability 0 of hitting sort of a delta function line. So line is missing. Here, line is missing for the same reason. This is eventually going to improve. And let me see, what will happen here? Still, on average, 4/10 turned on, but more noisy. Right? Because if they were actually in columns, it's sort of going to be regular, on, off, in a sort of a repeating pattern. Right? Whatever happens in this 10 rows is going to be the same in the next 10 rows. If this slope was, you know, what is it, 1/10 or something. Or however many rows. If it was 7 rows that it took to get from here to here, what do I have? 1, 2, 3, 4, 5, 6, 7. Maybe in the 8th or 9th row. Maybe in the 8th row, it looks like the first row or something. Well, I guess maybe it's, well, maybe this is row 0, 1, 2, 3, 4, 5, 6, 7, 8. So by the time it gets over to the next one here, it's going to sort of look like there. So it's the slope rather than the width that determines the repeating cycle. But if it's an integer, it's repeating. If they were random, it wouldn't do that. The distribution of which pixels were on would be sort of more random. You wouldn't see the repeating pattern. Okay, so I have to remember if I make a handout like this next time to add that as a case, because we talked about jittered sampling. Now, suppose we had area sampling. I'm going to call it area averaging. So what that means by area average, I mean the true integral, which, you know, if you could take enough samples, your Monte-Carlo sampling would get. So this is the limit for infinitely many samples, is if you did the analytic integral. And that you can approach by having more samples. So this is going to be a smoothly anti-aliased edge. Because this analytic integration is actually going to compute the area of this triangle or of this trapezoid and get the true fraction of this pixel that should be white. And so that'll totally remove the jaggies. As the columns proceed, you'll get a smooth change. And if you had a vertical segment moving, which is probably another row I should add to this table, instead of suddenly jumping from here to here, it would gradually fade in. which is basically what's happening down this almost vertical line, if you think of time being these extra columns. Now, what happens to this nearly vertical, infinitely thin line? Considering that the integral, say, across the x direction is integrating a delta function, which is infinite so that its integral is 1. That means on each square, maybe I'll draw the picture here. I should have left room for one more here to make it fill up. Okay. So the other line is sort of going through like this. It's not nearly vertical enough. But on most squares, it's going to integrate to this length, right? Which, you know, say, I guess it's infinitely bright, but if its brightness integrated to 1, this would be a little bit more than 1 because it's tilted. But say it compensates by being a little dimmer than perfectly white, and it integrates to 1 on each of these columns. So we have long stretches when it integrates to 1, and so all these are going to be bright. If we're have a position like this, maybe this one is very dim, and this one is a little bit brighter, so that the total intensity of both of these adds up to bright, completely bright. And then there's going to be another long column of completely bright. So basically, except for these potential rows where, you know, in this case, you'd hardly see this triangle, and it would be mostly this one. You'd hardly even notice that this was partly gray. But sometimes there'll be partially gray, but so I'll say jagged pixel-wide line, some other gray pixel pairs, why don't I call them, in a row. But mostly just, it's going to look jagged, right? So even though our perfect area averaging, even if you did that thing on this infinitely thin line, it would still look jagged. And actually, a moving vertical infinitely thin line, let's see, what would that do? That basically is going to have the result of successive columns here, right? As long as the line is in this region, it's going to be, if it's perfectly vertical, actually, it's only going to be in one column of squares. So it's going to be a line here and then suddenly jump to a line here. And then suddenly jump to the next. So it's sort of doing to that line what this thing was doing to my vertical polygon edge. So let's see, line jumps. Fills one column with white, and that column jumps. And let's see. What's going to happen with this one? Okay, that's something like this, the analytic average, right? Well, when all these pixels, that still integrates to 1. Right, because I've changed this brightness so this trapezoid adds up to 1. Because it's still going to, if it's going to, I mean, you can make any brightness you want. So, but these columns will all be bright, even though we're doing area averaging. You know, we may be lucky to have a little bit of intensity in here and a little bit less here. And then we're starting over with another column completely bright. So it's not that much better. So how can I say it? Jagged pixel wide line. Basically, it's the same thing. Some rows with 2 gray pixels. Okay, now, the whole point of this is to show why that triangular filter from last time was better. Right? Because basically what we're going to do now is, say, instead of, in the case of area averaging, the frame buffer, what do I call it, color X, Y, is, well, why don't I call it color IJ? That's for a pixel. The integral from, how can we say it? I minus 0.5 to I plus 0.5, integral j minus 0.5, j plus 0.5 of the color x, y, dx, dy. And in terms of a filter, that means I can write it as the convolution of c, x, y times this box filter of x minus I or I minus x. I'm assuming it's similar. But if it's the bf of x, y, which is the integral from minus infinity to infinity of the color x, y times this box filter of I. It's actually I plus 0.5 is really the pixel center. If we think of the box filter as going from minus a half to plus a half. Right, and that's because our box filter looks like it's left over from last time on this board, but that's maybe the previous class today. Goes from minus a half to a half, and here from 0 to 1. It has area 1, say. And what I'm proposing instead, let's see, I might want to keep this one to draw on, is to use the triangle filter right, this box filter, I write it like that. That's really the product, right, of 2 box filters, one in X and one in Y. It's only non-zero if you're within a half of the pixel center here. So it's integrating over this area. That's the area that it's non-zero on. So I can really write it as this box filter in 2 dimensions is the product box filter of, why don't I write it here? This is box filter in X, box filter in Y. And the same thing I'm going to use for triangle filter. So if it's linear in X and linear in Y, it's going to be bilinear in both of them. It's like its graph. The graph of this one in X and Y is like over the unit square, it's 1. Some of these lines should be dotted. And 0 elsewhere. So it's like this I should have used the eraser to make them dotted, and I wouldn't have clouded the whole blackboard. Now this eraser isn't clean enough. You know what I'm trying to draw. But now, what I want to draw here is the tent filter in X times the tent filter or triangle filter in Y. See if I can do that. That's a little harder to draw. So it's non-zero between -1 and +1. And in this plane, it goes up like a triangle. And in this plane, it's non-zero between -1 and +1, and it goes up like a triangle too. But it's the product of those two. So like along the line, here's x, here's y, and here is x equals -y. It's actually going to be the product of two things. It's going to sag down like a parabola here. And basically, it's what happens if we take this line here of slope 0 and gradually increase its slope, right? We're going to get sort of a ruled surface like this. And similarly for here, you can start to think of this as a horizontal line gradually increasing its slope to 1. If we take a cross-section, it's like that. So we have 4 copies of this sort of sagging tent thing. So it's called a tent filter, where T of x, I think I wrote that on the board last time, and I see if I can reconstruct it from memory. It was, it had to, between -1 less than or equal to x less than 0, it had to increase to 1. So I think that's 1 plus x. And then 1 minus x is going to decrease from 1 to 0 as x goes from 0 to 1. Actually, these agree at 0 and 0 otherwise. Which means that this convolution x, y, convolved with color x, y, the convolution evaluated at pixel I, j, is the integral from -∞ to infinity dx, integral -∞ to infinity dy, f of x, y, tent filter of I plus 0.5 minus x, tent filter of j plus 0.5 minus y, right? You put this thing centered at ij. So if here is the ijth pixel, this thing is actually non-zero completely inside a square of side 2. It's most weight here, but we have more weights on the others. So what's that going to be? What's the effect of that going to be? So what did I call this? Convolution with 2 pixel wide tent or triangle. It's a product of 2 triangles filter. So what's that going to do to this edge that was already anti-aliased? When this edge was anti-aliased, if it was almost vertical in most columns, see, maybe I've got room on this picture now to draw it. So let me draw an edge here between white and black. Okay, so in columns like this, it's going to appear here, and it's going to be, when I draw that same picture around here, for the next one over, it's going to be dark. In this one, it'll be entirely dark, right? This one I was drawing for this center, it's entirely outside of here. So if it's almost vertical, in most columns, it's going to affect only 2 columns at once, right? In this one here, if it's to the left of the center here, for these whole, for this filter, how can I say it? Right? If it doesn't cross this center line, which it won't in most columns, it'll only affect 2 columns. And it'll gradually fade from out of one and in the other. But occasionally, it will affect 3 columns. So basically, you sort of get a wider blurred line. It's still smoothly anti-aliased. It's not jagged anymore. Before, So the polygon edge, I'm sorry, I'm talking about a line now. I guess I was talking about a polygon. So the polygon smoothly, actually more smoothly anti-aliased, but some rows have 3 gray pixels. In terms of this infinitely thin line now, this infinitely thin line is now going to be anti-aliased. In most columns, it's going to overlap 2 of these filters and gradually fade out in one and into the other. So into this infinitely thin line, it took this triangle filter even to make it anti-aliased at all. Now smoothly anti-aliased. Usually only in 2 columns, sometimes 3. Okay, moving vertical infinitely thin line. It's not going to jump anymore, right? It's going to smoothly move across. And what was my last one? Yeah, this is going to move smoothly too. So this is why convolution with a 2-pixel wide filter is even better than just area averaging, if you could do it analytically. Well, since our sampling method, Monte-Carlo method of evaluating that integral, is going to converge to the true integral. That means if you take enough samples, you can get this behavior with Monte-Carlo integration, including the Monte-Carlo integration using jittering. But there's a problem with that. So let me so we're trying to estimate this integral, right? So can estimate by, I'm saying jittered because it could be optional. So that's going to be the 1 over n times the sum of f of x, I, y. Well, let's just call it xk, yk times h of I plus 5 minus xk. No, this 10 filter. I've already got my f. Maybe what should I've called it f in mine. I've called it c here. So let me call it c. C is the true color you could get by ray tracing from this subpixel sample. And this was 10 filter. I called it on my board. I think that's what I called. Right, and you could make these xk and yk be jittered samples if you wanted, or just totally, let's see. Actually, there'd be 2 ways to do it, right? You could try and choose them with probability proportional to this, using the cumulative distribution function. In which case, then that probability would cancel this, and you just get this one. So which method do you think is better? To choose them uniformly? Well, first of all, right? The jittered would get more complicated, right? Because to get jittered cumulative distribution functions, you'd have to make area proportional. Well, I guess the product, right? So you could, if you wanted to have, where's my, I never drew a graph of a single triangle here. If I have a triangle like this, I'm trying to make jittered samples to get equal areas, then I get them closer together here and farther apart here. So this doesn't even look equal areas, something like that maybe. So this is big and this is smaller. You could do that in both directions. Or you could choose them uniformly and then multiply them by these weights. Which do you think would be better? Well, for slowly varying color, if you're only estimating this answer at 1 pixel, and your samples are, have probability, this factor, then the things you're adding up will all be close to each other. You'll sort of cancel this variation by the filter weight, and since each sample has less variance, your integral will have less variance. So that way would be better for 1 pixel at a time. But if we did it this way, we could reuse these samples, right? Suppose we picked, I don't know, say 4 by 4 in here, so really 16 subpixel samples for here. We did the ray tracing for those 16 subpixel samples. Actually, what we need is, there are actually 2 more columns here. It's really 8 by 8. We need 64 samples per pixel. And if we were choosing them more likely closer to the center and less likely here, the jittered boxes would be different for adjacent pixels. But if we put them in the jittering like this, for this square, for all these other squares, we pick them equal, then this guy gets used for, I guess, 4 different things that overlap this pixel, right? Because I have the box for this one, maybe more. I guess it's only 4. This pixel center, this pixel, maybe, yeah, 4. This pixel center, this pixel center, this pixel center, and that, 4 of them have their filter overlapping this, which means I only have to do 1/4 of the amount of ray tracing, because I can reuse these pre-computed jittered samples for 4 different methods of estimating those integrals at 4 adjacent pixels. So in that case, that outweighs the extra variance you'd get, because you can afford to do 4 times as many samples. But there's another problem. Suppose you have a uniform area, say uniform gray or uniform white. So this constant is always 1. Well, if you were doing a good estimate, since the ray tracing is always going to get you that uniformly white wall, you'd expect, no matter what you did in terms of sampling, you would get that uniformly white wall. But this won't give you a uniformly white thing. Because although, take away this factor, this thing integrates to 1, this is only a Monte-Carlo estimate of that integral. And this product is not a constant function. So you're going to still get noise on a white wall using this Monte-Carlo estimation. And that's not what you want. So there's a way to cure that. Can you think about what could cure that? Suppose you compute this sum and you divide it by the average weight. Actually, we don't need the ends anymore, right? Because those ends cancel. The same sum of just the product of the filter functions. Triangle filter of j plus 0.5 minus yk. Right? So we're taking a weighted average now. And And so we're dividing by the sum of the weights, and that means if this color is constant, we're going to get exactly that color. And that way, you get rid of the noise on constant color regions. But because this expected value of the numerator is the true color, and the expected value of the denominator is 1, if you take enough of these samples, you're still going to converge to the right answer, even though you sort of, how can I say it? This might not be an unbiased estimate if you take a small number of samples. But there's another word for something that if you take enough samples, it'll still converge to the right answer, even though it's a biased estimate. Consistent, I think, is the word. And so this dividing by the sum of the weights is a consistent way of estimating the color. In the limit, it'll be the true color, but it'll get rid of some of the noise on slowly varying intensities. So how can we do that in an actual code? Where will I put it? I don't want to erase my beautiful chart here, so I'll put it here. So this is just, since I took the trouble to write it down. Oh, before I do that, just to make sure that I get time to say it, for the homework, I'd like you to give me 4 different kinds of pictures. So what it's going to say is anti-aliasing, depth of field, maybe 5, motion blur. So I want one picture with no, which is basically the picture you would have gotten on your first assignment. And then for the second case, I want yes, no. Yeah, and you don't have to do this. I think some default was 2048 by 2048 in the input file that was in that directory. But there's no point computing at that high resolution. Then I have to magnify it to even see whether you did anti-aliasing. You know, do something that'll fit on my screen without magnification, maximum 1,000 by 1,000. Or, I don't know, I guess I have a border around my viewing window in my EOG. So like 800 by 800 should be your maximum. So I can see the whole thing without trying to blow it up like I had to do on the first assignment. And then no anti-aliasing, but yes, depth of field. And for depth of field, you should experiment, right? The width of the circle in camera nomenclature, that's the f-stop, how wide the angle is, what's the ratio of the diameter of the lens opening to the focal length of the lens. And so just experiment with different ones, so probably, or several, is better, but no motion blur. And then one with only motion blur. There could be several different speeds, too. And then maybe one or more with all 5. Okay, and the other thing I wanted to say is concentrate on doing these effects. I suggest that you also include polygons. But I won't take off too much if you don't get the polygons going for this assignment. Just at least get, I forget, it was due today or next, or Friday? Friday. You know, if you're up against a deadline, don't worry about doing the polygons. Yeah? Question? One thing you can do, like if you want a room, it occurred to me, you can get a room by just taking 6 infinite planes. And then when your ray hits the closest one, it'll hit the floor when it's supposed to, even though if it could continue, it would also hit the wall. So you can still get a room-like environment. You're going to need a room-like environment for the third assignment because I want to see color bleeding, say from one wall to an adjacent wall, which is a typical global illumination effect. But say in your README whether you did polygons or at least general triangles, because even though I can't see it in the picture, if you've done it, I'll give you full credit. But I'll take off at most 1 point for not having done it, just to make your task a little easier and concentrate what's really important. Okay, so I think I still have time to write that little bit of code that I promised. So for all jittered, the jittered is optional, but let's just say we did it. Subpixel samples, say xk, yk. So we're going to do ray tracing for the subpixel samples over the whole screen. We'll trace ray and compute color. And then, well, I guess I should say for all pixels, initialize color equals 0 and weight equals 0. And then our outer loop is going to be over the subpixel samples, and the inner loop is for all pixels under the footprint of TF I plus 0.5 minus xk TF j plus 0.5 minus yk, right? This is all pixels I, j. In general, there'll be 4 of them. I guess if it's exactly at a pixel center, I guess it'll only be 1. But you know, if you do it randomly, it's unlikely to happen there. What are you going to do? So the weight is this product, right? That's this. You evaluate the 2 triangular filters to get the weight, which is the weight you're going to use in the weighted average. And what you're going to do is build up this sum and this sum over all pixels that subpixel jittered sample could affect in this computation. So color I, j plus equals, what did I saw? Compute color times weight. Weight times the color you're incrementing for all those pixels that subsample affects, and the weight of that pixel, the W. Okay, so this is for all subpixels. So, and then this is the sample loop. And then we have one other loop over all pixels. Where we just divide color I, j by weight. Right? So we accumulate in the inner loop the contribution to all the pixels that our subpixel sample can affect, and then we divide that by the sum of the weights. So, you know, I wrote it in this way because I was trying to get the formula on the right board, but this could be any filter function. Could be like the quadratic one that I talked about that was even wider, that's going to give you even smoother anti-aliasing. I'd have to think carefully, but let me think about that. If I had a vertical infinitely thin line, it would still move smoothly. I can't think right off why that even wider filter would help, but it certainly takes away even higher spatial frequencies. It's a better anti-aliasing filter, even though it has more blur. So vertical lines then would be 3 columns wide, a little more blurry, but probably even less aliasing on things like picket fences, where if you think about it carefully, even this triangle filter can let in some aliases because of the way it can overlap our pickets. You have to think about that at home. I don't have time in 30 seconds to draw the picture, but it can happen on a picket fence. And so in that case, that even wider filter might help. So that's it for today. Now I used up the time. We're back onto the schedule on the printed thing for next time.